Hello, everyone, and welcome to your, I think this is number, what are we on, 17 lecture for Historical Geology. This is the Proterozoic. We're going to be talking about all the geology that happened during the Proterozoic, which was a very long period. It was about 2 billion years. So we'll be talking about like 33% of Earth history today. So we're all going to cover it in one lecture here. And then next time we're going to get on to subject probably a lot of you will be interested in, I would imagine, be how life began on Earth. And that'll be next time. But today we'll be talking about what happened geologically during the Proterozoic. So the Proterozoic, you might remember, is one of our eons, one of our 4 eons. And this is a picture of Snowball Earth. A lot of geologists think that possibly Earth was totally covered in glaciers during the Proterozoic. So we'll go over some of the reasons scientists think that. It's just a hypothesis. It might not be true, but we'll go over some of the evidence and you can decide whether it makes sense or not to you. So you know that we have our 4 eons here. There are the 4 eons on the left-hand side, okay? And right now we are in the Phanerozoic. Welcome to the Phanerozoic. So you're in the Phanerozoic right now. And the 3 eons that preceded the Phanerozoic are the Proterozoic, Archaean, and Hadean. We've already talked about the Hadean and the Archaean. We're done with them. So now we're going to move on to the Proterozoic. And what's kind of crazy is after this lecture, we have covered over 75%, maybe even something like 80 or 90% of Earth history, okay? Because we just don't know very much about what happened during the Proterozoic and Archaean as much as we know what happened during the Phanerozoic. So like I said, we're always looking at the past of Earth dimly through a mirror because we only have little traces of what might have happened during those times. So we don't know everything. We don't even know 1% of what happened during that time. But we don't even know 1% of the species that have existed over time. You know, we know just little tiny snippets here and there. So everything is seen sort of darkly and dimly, but we get enough through the little traces of light that we see to get an idea of what life and Earth might have been like during that time. So we have covered everything in the Hadean. You know, we talked about formation of the moon. We talked about, we haven't talked about first life. I'm not going to talk about the heavy bombardment, but we haven't talked about first life. We haven't talked about photosynthesis yet, but we've covered the Hadean. We've covered the Archaean. We'll be done with the Proterozoic. And look at that. We're going to talk about 44% of Earth's history was during the Proterozoic. It was a whopping 2 billion years. So all the way from 2.5 billion years ago to 542, that ever important date that you must remember for this class, 542 million years ago, okay? It's only like plus or minus a million, so you don't have to know it exactly. So if you say 541 or 542 or 540, that's fine. Okay, so anyway, we'll talk about the Proterozoic here today. And what's crazy is that after that, we've talked about 75%. Actually, with the Hadean, you know, included, we've talked about like 90% of Earth history. Isn't that crazy? And we can cover it all easily in one lecture. Or sorry, a few lectures. So now, you don't have to know these eras exactly, but we do split the Proterozoic into 3 eras: the Paleoproterozoic, the Mesoproterozoic, and the Neoproterozoic. I just want to introduce those items to you because I will kind of refer to them throughout the lecture, and I just want you to kind of, the way you should think about it is sort of like Paleoproterozoic is sort of the early Proterozoic, Meso is sort of middle Proterozoic, and Neoproterozoic is kind of the later Proterozoic, okay? So that's just the way that you should think of them, and as I refer to them throughout the lecture today, it's just kind of help guide your thinking during when I refer to them. So anyway, that's all I'm going to say about those eras of the Proterozoic. You do not have to memorize those for the test, so don't worry about them. It's just for understanding this lecture a little bit better. So the Archaean was a period, as I mentioned before, was actually an eon of intense crustal formation. So this is how the continents look right now. Okay, and you'll see that the parts that are purple are Archaean crust. So back in the Archaean, you can see about how much crust was around, and you can see that there was quite a bit, right? So all the little purple blobs represent Archaean. However, the sort of beige color here represent Proterozoic, and you can see that by the end of the Proterozoic and the Archaean, most of the continents, they were basically built, right? So we only have to wait until the Phanerozoic to get the green stuff filled in. But, most of the continents were there. And basically something like 80% of the volume of the crusts was built by the end of the Proterozoic. So this trend of heavy crustal formation continued into the Proterozoic. And again, I know that I've covered this, oh my gosh, so many times, but it's so important, and people have to understand it. So I want you all to understand and know how continental crust is made. It's a really important process because you are sitting right now on continental crust. If you weren't sitting on continental crust, you'd be underwater, and your computer and your phone wouldn't work underwater. So and all the things that you love about life probably would be very different, and probably you wouldn't even exist if we didn't have continental crust, because how could human life have began underwater? Well, I guess it's possible if there were mermaids and things like that, but the fact is that your life probably wouldn't exist and would be drastically different if there was no continental crust. So that's why you have to understand how continental crust was formed. Okay, so just to go over the process again, you have a subducting slab here, goes down into the mantle. Okay, there's a subducting lithosphere. It starts to partially melt the mantle. How does it do that? Well, over the years, a lot of the ocean water seeped into the crust here. Seeped in. And as that downgoing continental crust, ocean crust is subducted, it gets pressed by the high pressure in the mantle and the high temperatures, and the water is expelled. It's dehydrated. The slab is dehydrated. The water is expelled out into the mantle. Now, a lot of people make the mistake by saying, oh, the water's so hot, it melts the mantle. No, that's not it. Okay? That's not it. What happens is the water lowers the melting temperature of the mantle. Okay, there it is. Lowers melting T of mantle. Okay? That's how the mantle melts. This is an amazing process because we do not change the temperature of the mantle, but we melt it. Isn't that crazy? I bet a lot of people didn't even know that you could melt something without changing the temperature, but you can, because if you ever remember salt on ice, you can throw salt on ice and melt the ice without changing its temperature. So, anyway, that's how you do it. You melt the water by lowering the melting temperature of the mantle. Okay, that produces. What happens is that produces basaltic melts. Okay, so the basaltic melts get kind of stuck in the mantle. They make these dikes and sills. They make these plutons and batholiths. And what happens over time is you get so much basalt injected into the crust that eventually the basalt partially melts and it creates andesitic lavas. Okay, that is andesite intermediate. Because remember, the continental crust on average is intermediate. It's not mafic like the ocean crust. Okay, so it's very important you understand all those details. And you have to understand, I'm sorry to say, all of those details. This whole process of lowering the melting temperature to form the mantle is called flux melting. Okay, flux melting. That is how the continental crust is formed. And what is amazing is that you could not form continental crust without the aid of water. If there was no water on Earth, you wouldn't get continental crust. And that is why if you go to Mars or Venus, maybe one of you someday will go to Mars and Venus. I don't know. It's the 75 years in the future. Who knows? But if you go to Mars or Venus, Mercury, there's no continental crust. Why? Because there's no water. That's why. Okay? So you have to understand that. It's very important. Let me see. I want to erase everything on here. And, oh, I guess I'm moving on. Okay, so a single subduction zone forms a volcanic island arc. Okay, so these volcanoes here are referred to as a volcanic arc. So you get an island arc, volcanic island arc. And we call it an arc because it's arc-shaped. Yep, that's why. So you can see the Aleutian Islands off the coast of Alaska are arc-shaped. Okay, it's the shape of a subduction zone. You can see that the Japanese islands are kind of arc-shaped. Okay, so that's why we call it an arc. You can see the back arc basin here, the back arc basin behind Japan, right? That's where we think, for example, the greenstone belts, the kind of environment greenstone belts of the Archean were formed in. It gives us proof that plate tectonics was happening in the Archean. Also gives us proof that there was water around in the Archean, okay, and water in abundance. So here we go. We have the subducting ocean lithosphere. It's being crammed into a continent. Now, one of the main ways that continents accrete together. So we all start off as kind of these volcanic island arcs, okay? So all continental crust starts off as a volcanic island arc like the Aleutian Islands or the Japanese islands, okay? Now what happens is this process to build up bigger continents. What happens is this process of accretion, okay? So accretion. So accretion is when you have these island arcs converging and colliding with the larger continental mass, okay? And that forms in a subduction zone. So you can imagine these volcanic island arcs are being tooting along with the subducting slab, and as the subducting slab subducts, the island arcs collide with the rest of the continent, okay? Creates this major collision, and the island arcs are sutured onto the pre-existing continental crust. Okay, so after accretion, that's what it looks like before accretion. You have that island arc right there, and then after accretion, you can see that it's been glued together. So you all see that? So here's the accretionary wedge. This is all the sediments that get scraped off of the bottom of the ocean floor as the subducting slab collides. This is the pre-existing continent. This is the new volcanic arc. So look what happens to these things when we glue them all together. So the accretionary wedge gets kind of thrust up in this new type of rock. By the way, we call this rock melange. Okay, it forms a special rock called melange, which melange is French for a mixture. So it's a mixture of a lot of different complicated ocean sediments, okay? That have been subducted, often to exposed to high pressure, low temperature metamorphism. Okay, so a lot of times in these areas you find a rock called blue schist, which I talked about. That's in our lecture number 7, the metamorphic lecture. Right, blue schist is a high pressure, low temperature rock, high P, low T. Okay. So this is the volcanic arc, the old volcanic arc, and you see it's been sutured or glued onto that pre-existing continent, and the continents become bigger and more mountainous. You see how you kind of have little volcanic mountains here, but after the suture you get these larger mountains created from collision along with volcanics. Okay, so that's very indicative of a accretionary zone, and this whole process is called an orogeny. Everybody loves that word for some reason. Orogeny. So an orogeny is a mountain building event. Okay, you want to write that down and remember that. It's an extremely important vocab word for this class, because we're going to be talking about, like, oh my gosh, orogenies. You're going to have orogenies on your orogenies by the time that we're done with the class, because there's so many of them. We're going to be talking a lot about orogenies today, about different orogenies. So you'll learn all about these. But it's just mountain building events, okay, that result from this process of accretion, okay? And there's accretion. Very simple. There's accretion, okay? Let me erase everything on here. You go. You got a volcanic island arc, subduction. The volcanic island arc glues on to the pre-existing arc. You get mountain building, and you get accretionary wedge buildup, right? You get the melange. You get mountains, you get volcanoes. Okay, so that's what you get with these accretionary orogenic orogeny events. Okay, so we call these orogens or mountain belts. Okay, oro, it's Greek for mountain. Genesis, it's Greek for origin. So it just means origin of the mountains. Okay, origins. So these mountain belts are often intruded by Plutons. So let me show that animation again. So there's still a lot of volcanism. Okay, this is what happens. The crust thickens up a lot. So look at the thickness of the crust. Okay, so here's before the orogeny. Here's after the orogeny. The crust gets thicker, right? You all see that? Crust gets thicker. So thicker crust. Okay, we're right, thick. Okay, it's thick crust. There's still volcanism, but a lot of that volcanism can't get through the thick crust anymore. Can't get through the thick crust anymore. So it emplaces itself as a magma body. So instead of having a lot of volcanics now, we get a lot of magma intrusions and plutonic bodies, right? Plutonic igneous rocks. So those big plutonic bodies are called Plutons. And they're just like big magma bodies, okay? If you get really big ones, big huge ones that are like regionally sized batholiths, like huge Plutons, we call those batholiths. Okay, so these are big regionally sized masses of magma. Okay, so real famous. So we're going to talk about batholiths and like real famous batholiths that are all over the world. These create some of like the big granite outcrops in the United States. Okay, so a lot of your beautiful granite countertops come from batholiths, okay? So whenever you're admiring your beautiful granite in your bathroom, maybe you don't have granite yet, but maybe when you're older and you have, real jobs, or you get, or maybe you're already older and you have a real job or whatever, but you get a beautiful countertop in your bathroom or in your kitchen or whatever, you can thank orogenies for that, because a lot of those come from orogenic belts. Anyway, so let's first talk about the Paleoproterozoic and some of the specific things, important things that happened during the Paleoproterozoic. And one of these really important things that you're really going to appreciate, because it's like very important for the history of our country, is Laurentia. Okay, so a lot of people, if you were going to explain the history of the United States, maybe you would start with, I don't know, you might start with Native Americans coming over in the 14,000 years ago, or you might start with the colonists coming over, and and Christopher Columbus or whatever in 1492. But really, you should start in the Paleoproterozoic 2.5 billion years ago, because that's really when our continent of became the United States, became America and North America. That's really when it started, right? Was in the Paleoproterozoic. We get Laurentia. So before we were called North America, this continent was called Laurentia. So I don't know why we don't call it North America, but we don't. So we call it Laurentia. So we start calling it North America like when we get to the Phanerozoic. So Laurentia is what one of a very, very important term that you should be very familiar with. But anyway, Laurentia was the first large continental landmass. So what's kind of interesting is that the country that you're living in is one of the oldest big continental-sized land masses that ever existed. Okay, so it forms the Craton of North America and Greenland. Remember that the Craton is the basement rocks that form deep underneath the sedimentary rocks and form kind of the basement and the core of the continent. So the oldest rocks in the world, of course, are in Canada, right? The Costa Gneiss. This was the first big continental-sized craton to exist, was Laurentia. Okay, North America. So you can see this beautiful little map of our country and Canada and parts of Mexico. And you could see all these different names. What the heck do all these different names mean? All the different names you see there, Wyoming, Superior, Cordillera, Yavapai, Mazatzal, the Ouachitas, the Appalachians, the Grenville, right? The Ray, the Hearn, the Slave. All those things are different orogenies. Okay, so they all refer to the different blobs of land that were created during different, sutured together during different orogenies. Okay, and by the way, Greenland, part of North America. Okay, beneath this part of the ocean here, excuse me, that is just continental crust. So we are one continuous landmass with Greenland. By the way, we're connected to Greenland. Okay, so Greenland is not its own continent. It's part of North America technically, and it's connected to us. It's just underwater, like the part that's connected. The little umbilical cord that connects us is underwater. Okay. So anyway, here are some charming little videos that are going to show you. These are amazing. What I'm going to show you is an amazing, it's hard for you to appreciate it at this time, but it is an amazing synthesis of science, of historical geology that shows the development of the continents over time. 1.5 billion years of history are recorded here. It's really like a miracle of science that we have things like this. So I'm going to show you, this is going to show you just exactly how all the continents changed position over time. Okay, and we all know this through paleomagnetism, which I will explain a little bit. Well, I explained a little bit when we talked about plate tectonics. You might remember paleomagnetism, and you might remember how we about paleomagnetic anomalies and things like that. So that's how we know all this information today. So here's plate tectonics 1.5 billion years ago to today by this guy, Sierra Scottis. He's just one of the greatest paleomagnetic scientists in our world today. So this is the Proterozoic. This is everything. This is all just happening in the Proterozoic. We don't get to the Phanerozoic by 542 million years ago. So this is actually, I'm going to stop it just for a minute. This is actually the first supercontinent, Rodinia. Okay, you can it's kind of weird because it's on either side of the globe, but you can see that all the continents are now connected, basically. So it's the first supercontinent we had, Rodinia. It's going to break up pretty soon. Doesn't last very long. Okay. Okay, so anyway, I think you get the idea. And look, we only get through, that's almost the end of the what do you call it, the Proterozoic, but I think you get the idea. So we end up, the Proterozoic ends with the formation and then destruction of the biggest the first supercontinent, Rodinia, and that breaks up by about this time, 750. You could see 785 million years ago. It says right here, 750 million years ago is when it kind of really started to break up. So anyway, just kind of give you an idea. This is so detailed, and probably you're looking at the moving shapes and you're like, what does this all mean? But it's really amazing that we know this much detail about where the continents were over different phases of Earth's history. So you might think, like, how on earth do they know things like that? But it's all through paleomagnetism. So I'll explain that a little bit later in the lecture. So let's go back here. Laurentia was the first large continental landmass, though. So notice how it's composed of these patchworks of different sections. Okay, so you see Superior, you see Grenville here, the Appalachians, the Cordilleran, the Wyoming, the Churchill, the Ray, the Hudson, blah, 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 right? The Slave here. There's the Wampanoag over here. I can't see it because of this little cloud bubble. But anyway, in blue, so these all represent different orogenies, okay? So different accretionary events where different pieces of patchwork land masses got accreted together to make the beautiful Laurentia continent. Okay, so the blue color that you see, the Appalachian and the Cordilleran, and I think this one down here, I can't remember which one this is, that we're actually on in South Texas, but that might be the Yavapai, or that might be the Yavapai, I can't remember. But anyway, the blue color is what you see. Those are Phanerozoic Aerogenes. Okay, so those occurred in the Phanerozoic. We're not going to look at those today. The green stuff that you see, all the way through the kind of yellow to the gray and the beige, those are things we're going to be looking at today. Stuff that's like this color, so the Superior, the Wyoming, the Hearn, the Churchill, the Ray, North Atlantic, those are Archaean Cratons. Archaean Cratons. So those were blobs that already existed. Okay, they already existed. Those were formed in the Archaean. Now we're going to talk about the green stuff, this color, the green, the gray, the oh, that's continental rifting. Oh, actually, that's a right there. That's the billion-year-old continental rift I talked about a little bit in class during plate tectonics. So you get the imbricated crust. Let's see, so that's Grenville Orogeny, things like that. So that happened during the Proterozoic. So each of these sections are called terrains. They are accreted together during different orogenies. Okay, so much of the Canadian Shield, which is northern U.S. and Canada, consists of Archaean Cratons that accreted together in the Paleoproterozoic. Okay, so a lot of that material was already there, but then it came together and got glued together during the Paleoproterozoic. So the place where there was really a lot of growth to Laurentia was to the south, and you'll actually see the Laurentian continent continues to grow to the south, right? So the Yavapai, I think it's Mazatl, Yavapai, Mazatl, and the Grenville Orogeny are big orogens that occurred during the Proterozoic. So these two, the Yavapai and the Grenville, were big orogenic events that happened in the Mesoproterozoic. The Appalachians, however, were during the what do you call it? The Phanerozoic eon. Okay, so just to kind of give you an example of how these areas develop geologically, we're going to take a close look, very, very close, detailed look at the Wampanoag orogeny here in northern Canada. Okay, so let's take a look at that terrain. So the way that these, so the Wampanoag gives us a very good example of something called the Wilson cycle. Okay, the Wilson cycle is a cycle of continents being rifted apart and then coming back together with the opening of a new ocean and the subsequent closing of that ocean. So if you can imagine these cycles take billions, of years. I mean, not billions, hundreds of millions of years to complete. But it involves the continent rifting apart, creating a new ocean. That ocean being born, living, dying, and being closed up again. And it creates one Wilson cycle. Okay, and it creates a very special series of different rocks that we're going to explore right now. So first of all, we start off with your normal everyday continent and ocean crust. So you have granodiorite, you have some basically a dioritic intermediate crust, okay, and then you have continental crust, and then your ocean crust is basalt, of course. So what happens is we start off with rifting. So we're going to start to rift this continent apart, okay? So the mantle is going to be convecting here underneath. It's going to start to extend this area. So you're going to get all of this. You got to get all this crustal extension. Okay, it's going to start to create a divergent boundary. You're going to start to get partial melting to form basaltic rocks up here, erupting basaltic rocks, and you're going to get lots of Plutons in place and lots of rift valleys. Okay, so you can see you're creating a rift valley there. So that's continental rifting. The next stage, you get the beginnings of an ocean, early ocean basin formation. Okay, so you get all these near coastal shelf sediments, sandstones and siltstones, maybe some shale on either side of the continental, basically the continental shelves. Then you get in the middle the beginnings of an ocean, right? So you have some new baby ocean floor forming right there, right? So then the next stage is kind of like a full ocean basin, right? So you have your basalt underlying the ocean basin. You get a series of sandstone. On the shelf, you get a series of sandstone. So that's the coarser sediments. Then you get finer sediments like silt and clay that forms a shale. And then out in deeper water, you get coral reefs that start to form limestones. Okay, so you get the series. This is a very important series of rocks, guys. You have to know this. Sandstone, shale, limestone. So as you get deeper and deeper and deeper water, you get that. Let me just draw that really quick. So if we have, here's our water level. Okay, and here's I'm going to draw our continental crust here. Okay, so here's continental crust. Okay, and then it's going to go off into very deep water. That's the slope. Here's the continent. Okay, so when the water is very shallow, we get a lot of sand. Okay, so right here, you lay down sandstone, right? So we get sand. When the water gets deeper, finer and finer particles settle out of the water. So then in this area, you start to get siltstone. Silt and clay. So you get siltstone and shales. And then when you get into deeper water, you start to get a lot more like coral reefs and different marine animals creating reefs. So with the reefs, you get limestone, okay? So that's the limestone. Okay, so that's a really important sequence of rocks that we get. And they represent kind of shallow water, medium water, and deep water. Okay, deep marine waters, okay? So you should know that. I'll talk more about that later. So anyway, we start to see that build up, that sequence of sandstone, shale, and limestone on the edges of the continental margins here during the Wilson cycle. So then the next part is we start to get, after the basin, we have a full ocean basin. At some point, this divergent boundary stops. It stops convecting here. Everything gets kind of cold and old. It's not hot anymore, and the ocean lithosphere starts to sink, and we get subduction. Okay, so we get a subduction, we get a volcanic arc basically. So we get volcanic arc here. And we get, that forms right in the middle, right, between these two continents that had already split apart. So what's going to happen? Well, this is going to move. This ocean basin is going to close, right? So it's going to close. So this continent, this whole continent right here, is going to move this way. This volcanic arc is going to be moving this way, and there's going to be a collision between this volcanic arc and this older continental terrain. And what is going to happen? You tell me what's going to happen. If you're thinking to yourself, an orogeny, you're right. So you're going to get an orogeny. You're going to get a suture between this volcanic arc here and this terrain over here. Okay, so I'm going to erase everything. As time goes on, you see you get the collision of that volcanic arc with that continental area. You can see that all of this formerly marine sedimentary rocks, right, the limestones, the shales, the siltstones, are now thrust up on top of the continent, and they create mountain belts. Okay, you can see this volcanic arc has now created a mountain belt as well. Okay, and so now you have this accreted terrain, arc-continent collision. And what happens? Well, that stuff starts to erode. So now you see that it's eroded, it's flat. And we get another subduction zone form over here as, again, the crust gets cold and old, it starts to sink. And now we're going to have movement and collision of this continent with this continent. Okay? So they're going to accrete together as that ocean basin closes. And that's how we get, and it's going to erode like that. And that's how you end up with a complete Wilson cycle. Okay? So it's pretty crazy that, think of how we started. We started off with a single continent, right? It opens up. It spreads out, the crust, the ocean crust that was created gets cold and old, subduction starts to occur, it collides, and it collides all together and closes up, and we end up with, again, those original continents sutured back together, but we get a lot of, complicated geology in between that is indicative that, hey, at one time there was an ocean basin, but it closed up. So it's amazing. The Wilson cycle is amazing because it takes 1 billion years to complete. Right? You have to create a new ocean. That ocean has to get old and elderly, and then it closes up again, and you suture those original continents together again. So that's the Wilson cycle. It's pretty amazing, if you ask me. So again, I just want to emphasize that marine sequence of rocks. So again, you get this limestone, shale, sandstone sequence. The sandstone forms in the shallow seas. The shale forms in kind of medium depths, and limestone is very, very deep. So it's kind of cool because what you'll often see in a certain area is a sequence of sandstone on the bottom, shale on top, limestone on top of that. So again, remember our principles of superposition. Look right here. Okay, if we were right here, we'd find sandstone on the bottom, shale on top of that, limestone on top of that. So what does that mean? It means that the water was getting deeper and deeper and deeper at that area at that time. Sandstone forms on the coast, shale forms kind of offshore, limestone forms very deep waters, marine waters, okay? So it means that the waters were rising. Okay, that is called a marine transgression. Marine transgression. The water levels were rising. So when sea levels fall, that is called a regression, and when they rise, it's called a transgression. When we have a regression, we see the opposite. We see sandstone on top, and then we see shale, and then we see carbonates, right? Limestones. Okay, carbonates are limestones here. Okay, so that's how you recognize a transgression, right? You'll see sandstone on the bottom, shale on top, limestone on top of that. Okay. And remember, it means that water levels were rising. And you'll find that over Earth's history, oh my gosh, water levels rose and fell, rose and fell, rose and fell 1 million times. You know, it happens all the time. So I mean, people are very worried, and I mean with due reason, that water levels are rising. But at the same time, it's a process. Water levels are not constant. They rise and they fall. They rise and they fall. So it's not like Earth hasn't been through that before. Okay, humans haven't. Well, actually, humans have been through major climate change before. But right, I mean, gosh, going from the Ice Age to the interglacial period, but still alarming, of course. But and it'll still require us to adapt hugely. But Earth has gone through many cycles of water levels rising in a transgression, water levels falling in a regression. Okay, so it's happened many times over Earth's history, and you have to be very familiar with this process and with the sequence of rocks that you find, right? Sandstone on the bottom, shale on top, limestone on top of that. And if it's flipped, it means a regression. It means water levels are falling. Okay. So a lot of Proterozoic rocks are just this. They are what are called sandstone. Just like, remember for the Archaean, we had two kind of basic types of rocks that I wanted you to know, right? We had the granite gneiss complexes, and then you had the greenstone belts. So for the Proterozoic, you should be familiar with the sandstone carbonate shale assemblages. Okay, and again, these are indicative of rising and falling water levels. So these were deposited on passive continental margins in intercratonic basins. So they were deposited on top of continental crust, places where continental crusts were inundated with water, underwater. And they are the most common Proterozoic aged rocks. So most rocks from the Proterozoic are these sandstone carbonate shale assemblages from rising and falling sea levels. Okay. Some very famous ones. Some of the carbonate rocks, like dolomite, dolostone, such as the Kono dolostone in northern Michigan, contain abundant bulbous structures. So you see these bulbous structures here. Okay, you see these. These are very important. You might be looking at this like, what does that mean? Boring. What is that? Why does it matter? Hey, show some respect here, because those things are stromatolites. They are some of the oldest traces of life that we have on Earth. Okay? So, if evolution is true and correct, at some point, hey, your great whatever grandfather could have been a stromatolite preserved in the rock here. So anyway, it's very important that we see these structures. Anyway, we'll talk more about that, and we're going to talk a lot about stromatolites next time. We talk about origins of life. But anyway, here's Laurentia again. Okay, so this is what became the North American continent. This is the part of Laurentia that would have existed during the Proterozoic. Okay, so you see I just kind of blanked out the Phanerozoic Aerogenes there. So this is what Laurentia, this is what North America would have looked like during the Proterozoic. Okay, so let's talk about this guy. This is a really big, important orogeny that happened during the Proterozoic called the Grenville. Okay, the Grenville was a major worldwide event. It created the first supercontinent, Rodinia, which existed from about 1.1 to 1.3 billion years ago is when it started to suture together. So the Grenville orogeny, now, this is another thing. I'm going to kind of turn things here. The Laurentian continent was not oriented the way like this, right? It has twisted and turned over time. So during the Proterozoic, it would have looked more like this, okay? So it was turned about 90 degrees on its side. So the Grenville orogeny would have been kind of on the south, maybe even southwest side of our continent, okay? So here's Laurentia. This is, like I said, you see how this is turned? Okay, so this is Laurentia right here. Okay, you all see that. Let me change the color of the pen so it pops out more. Okay, hold on a second. My cat is meowing. It's really annoying me. Just 1 second. I gotta go get that. Okay, sorry, I'm back. Those cats are just like, you give them everything they want and they just want more. They just insatiable. I guess people are like that too. But anyway, I locked her outside. So where was I? Oh yeah, Laurentia. So you could see how Laurentia is turned on its side here. Let me get rid of this guy. Yeah, okay, and the Grenville Orogeny is happening here on the south side. So this, again, this represents Grenville Orogeny stuff. And you can see that that orogeny, oh, where's my pen? There it is. You can see that orogeny was happening between Laurentia and what at the time was called Amazonia, Baltica, and the Congo. Okay, so these are basically cores of, so this would have been, Congo would have been about like middle of Africa. Amazonia would have been kind of like the core of South America, and Baltica actually would have been like the core of Western Europe. Okay, so these were all to the south at one time. You can see with the equator. So at this time, you know, 1.5 billion years ago, during the Proterozoic, during like the middle Proterozoic, Laurentia was right at the equator. Okay, and you could see that the Congo, South America, Baltica, so that would be Western Europe, basically, were to the south of the equator, and of course they're very, very different positions than they are right now, colliding with Laurentia. Okay, so there must have been a, let me get the ink off the page here. There must have been a subduction zone here. Okay, there was a subduction zone here, and it was bringing these continents into collision with Laurentia. Okay, so that's what Rodinia would have looked like about 900 million years ago. Okay, so you can see there's Laurentia right there. Here's another depiction of it, and as you can see, here's the, you know, the South Pole is right, like right, you know, Baltica is right over the South Pole at this time. Okay. So Rodinia did not last. It came together maybe like, probably started coming together like 1.5 billion years ago. And maybe it was in its full glory about 1 billion, right? 1.1 billion years ago, 900 million years ago. And then it broke up by 750 million years ago. It broke up. Okay, so just a question here, very important question. How do we know this? I think these are very important questions because people like just like, okay, that's what science says. But if you're going to be like skeptical at all and have any kind of questioning, inquiring mind, you know, or like a real scientific mind, you got to ask, like, how do we know this? How do we know this stuff? Because, you know, you should take it, and you shouldn't just take it on faith, right? It's kind of funny because most people take science on faith. You know, they just kind of, they take it on, they have faith, they have trust in what scientists tell them without even necessarily questioning it, you know. So, but we don't want to be like that. We want to have some understanding of how we even know this stuff. What's the evidence? Okay, because remember, in anything scientific, you have to have evidence. So let's go over a little bit of just giving you basic idea how we know where the continents, like the positions of the continents over time. How do we know any of this stuff? Like, look at this detailed map. Laurentia here, and West Africa, Greenland, Siberia, they're vastly different places than they are now. How do we know that? So the answer to this is we think these things from paleomagnetism. Paleomagnetism. So in paleomagnetism, you might remember that rocks often contain the mineral, that all-important mineral, magnetite. Magnetite grains align themselves with Earth's, you might remember Earth's magnetic field, right, which is created by the convection of the outer core. Did we have an outer core in the Proterozoic? Yeah, we did have an outer core. Remember, that was created during the Hadean. So we've had an outer core for a long time. So we have a magnetic field. Those magnetite grains align themselves with the magnetic field. So depending on the direction, right, they're always going to point towards magnetic north. They'll always point towards north. So we can look at very closely at how those magnetite grains are oriented, and we can get an idea of what the magnetic field was doing. So that gives us longitude. We can get latitude by looking at the inclination of those magnetite grains, how they were pointed, how much they are pointed down. Because at the equator, the magnetite grains will be totally horizontal. At the poles, they'll be pointed straight up and down. And anywhere in between, the angle of the magnetite grains, the direction they're pointing between the surface, and it's going to give us the inclination of and the latitude. So it'll tell us the latitude. Okay, so that's how we get these like GPS points practically of where the continents were located over Earth's history. Okay, so just another thing I want to talk about, events during the Proterozoic. I talked a little bit about the Grenville Orogeny. Another big event was possibly what's called Snowball Earth, okay, where the Earth was possibly totally covered with ice at one point during the Proterozoic. Why do we think that? Let me show you the evidence. Okay, these are some rocks from the Proterozoic, and they consist of very poorly sorted, well-rounded conglomerates with very big chunks of rock here, right? You could see very big boulder-sized chunks of rock. Look at how big some of these boulders are. Okay, those scream glaciers. Okay, these are, so I know we didn't really talk about glaciers in the prep for this class. Talked a little bit about them, but not too much. But these kinds of deposits are the kinds of things deposited by glacial till. Okay, so when you just look at this, it's glacial rocks. Okay. Now, this is the thing. We find rocks like this all over the whole world of Proterozoic age. And that's the thing. We find glacial rocks everywhere during the Proterozoic. Here's a map that shows them. Okay, look at this. 582 million years ago, we find glacial, basically glacial Proterozoic rocks all over here. Okay, shown in the yellow. Ignore the red dots, but look at the yellow dots. These are all glacial deposits. 635 million years ago, we find them, in Laurentia, in Africa, all over Asia, India, Australia, Greenland. 710 million years ago, we find them all over the place. Maybe the only place doesn't seem like we have any is maybe like here, kind of in Siberia. It doesn't look like we ever find any of those deposits. And gosh, that's like almost about it. Maybe here the tip of, but I don't even, you know what? I think this is all Phanerozoic crust anyway. I think northern Siberia here and the tip, like Argentina, and the tip of South America is all Phanerozoic stuff anyway. So I think that it's like these are literally worldwide during the Proterozoic. So that's why people are like, hey, we find these glacial deposits everywhere, covering the whole world. And that's why a lot of people think that at one point during the Proterozoic, it was Snowball Earth, the whole Earth was frozen, covered with glaciers. Okay? We don't know very much more than that. We don't know why. But I can tell you this, is that with glaciation, it's kind of like it's a snowball effect. Okay? It's a snowball effect. And you know what snowball effect means? It means that the snowball gets big. As the snowball rolls, it rolls faster as it gets bigger, and as it gets bigger, it gathers more snow, and then it gets bigger and it gathers more snow, and et cetera, et cetera, et cetera, and it's like a runaway effect. So glaciation can kind of be like that, because this is what happens when you cover some of the Earth with snow and ice. It vastly increases what's called the albedo. The albedo. What is Earth's albedo? The albedo is how much of the sun's rays are reflected back into outer space. So when you, for example, shine the sun on water, that water will absorb 94% of the solar radiation. And, you know, the surface of the water reflects something like 6% of it back. Because you all know, if you, gosh, you ever like fishing or you're at the beach or something and the sun is just going down or coming up, sometimes it's shining off the water. It's like blinding you, right? You know how the water can reflect the sun. But only about 6% of solar radiation is bounced back. However, when you have snow and ice covering the Earth, I don't know if any of you have ever been in a situation where it's like there's a new, freshly fallen snow. Oh my gosh, it is so reflective. It's crazy. It is so reflective that I don't know if any of you have ever been through this, but I grew up in, I didn't grow up in Michigan, but I went through grad school, in Michigan. And when you had like a freshly fallen snow in the middle of the night and you went outside, it was almost like daylight because there was so much reflection from the moon and from the lights that the light doesn't get absorbed, it gets reflected. So 90% of the sunlight gets reflected off of that snow and ice. And so what does that mean? It means that the solar radiation that should have been coming and heating up the Earth gets bounced back into outer space, and we lose the heat. So that's what I mean. There's a snowball effect. There's a runaway albedo effect where once the Earth gets somewhat covered in glaciate, kind of worldwide glaciation, it can bounce off all of that solar radiation. We can kind of get trapped in a glacial cycle. Okay, so things like that can happen. Anyway, snow and ice are very good at reflecting solar radiation. So that could have been something that caused the snowball effect, but we don't know. We just don't know because we don't have enough information. Like I said, and I keep saying, we only see these things very dimly through the past because we only get little traces of hints, little evidence here and there. And we can maybe see that there was a glaciation worldwide, but we don't know why or how it could have happened. Snowball Earth is not universally accepted, but I would say like a majority of scientists accept it. But anyway, let's move on to the next topic. Hold on one second. Okay, so anyway, sorry for the interruption here. Yeah, so Snowball Earth is not universally accepted. We talked about that. Let me get on to the next subject here. There we go. Oh, whoa, okay. Another very, 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 very important event we have to talk about here that happened in the Proterozoic was something known as the Great Oxygenation Event. Sometimes people even call this GOE. G-O-E. But these are some interesting rocks here. You see the red banded rocks right here. This is something called banded iron formation. I'm going to write that B-I-F. Sometimes it's called just Biff. Okay, banded iron formation. So this is a rock it's a rock from the Proterozoic. It's very characteristic of the Proterozoic. It's very beautiful, very interesting looking. Called banded iron formation, and it is indicative of the Great Oxygenation Event. Okay, so this is the time when oxygen finally became prevalent on the Earth. Okay, so this is Biff, or banded iron formation, quite common in the Proterozoic. So the rock consists of the red oxidized iron interlaced with this black reduced iron. So this is kind of oxygen poor. So I'm going to put O2 poor. And then the red you see is O2 rich. Okay. So they're both iron oxides, but one has more iron to oxygen, that's the black, and one has more oxygen to iron, that's the red. Okay. So basically the way that these things form is during the Archaean and Hadean, you had the oceans. There was a lot of buildup of iron in the oceans. Okay, so you had a lot of iron in the oceans. But during the Proterozoic, you started to get these photosynthetic organisms. And they were living in the photic zone of the ocean, okay, where you can actually get some sunlight, right? So the sunlight was giving the energy needed to do photosynthesis in the upper ocean. And basically these little guys were producing oxygen, right? So they're producing oxygen up here. So these photoautotrophs, photo means light, auto means self, troph means feeding. So these are light self-feeders. So they're ones that are using light to produce their food, which is what any plant does, right? Plant, or not any plant, but most plants use photosynthesis to produce their own food. So the iron is in the ocean is starting to react with the oxygen, and you get Fe2O3 and Fe3O4, the reduced black kind of iron. It mixes with the silica from the organisms. You know, a lot of the organisms are producing silica shells, so silica SiO2 shells, and that's mixing with that silicate is mixing with the iron oxides, and you get these bands of intermingling black and red silica and iron rocks, okay? And that's called banded iron formation, all right? So as the oxygen is released from the stromatolite cyanobacteria, cyano means green or red, or sorry, green or blue, right? The color, you might know the color cyan is kind of a greenish blue. Cyanobacteria, it's photosynthetic bacteria. So the stromatolites are making this oxygen that reacts with the iron in the ocean, and it indicates that suddenly there was oxygen in the atmosphere and in the oceans, and that was very indicative of life. Okay, so the great oxygenation event means that life was present on Earth, and we see the first traces of oxygen. The first very earliest chemical traces of oxygen we see in the atmosphere and oceans were right around here. So right around, this is 3 billion years ago, this is 2 billion years ago, right? The Proterozoic was, this is all Proterozoic, right? So we see the very first traces of life, maybe 2.5 billion years ago, we see the very first traces of photosynthetic life, okay? So the red line is the maximum amount of oxygen, the green line is the minimum. You can see that in the Phanerozoic, there were times in which there could have been a lot of oxygen in the atmosphere, possibly more than 30% oxygen. Right now, our current level is about 21%. Okay, so oxygen was low, but it was gradually building up during the Proterozoic. Okay, so you can see that oxygen levels are maybe just around, right around here, which is maybe like 3% oxygen. And then after about 1 billion years, they start to rise steadily. Maybe you're getting around 10% to 20% oxygen. And then after the end of the Proterozoic, they really start to rise to about the present levels. Okay, so where'd that oxygen come from? Comes from photosynthetic life. So our next lecture, we're going to be talking about where that photosynthetic life came from, and how we kind of got our origins, the very first origins of life. So that's going to be the next lecture. So anyway, that's all I have for you today. Hope you enjoyed the lecture, and I will talk to you next week with the origins of life.